Okay, so let's get into it. Today we're doing a deep dive on a really interesting piece of hardware that solves a classic problem.
A very classic problem.
We're talking about long-distance video signaling, and specifically the DVIgear DVI-7311 fiber optic extender. Our goal here is to really understand how this thing gives a much longer life to, good old DVI.
Right, and the challenge it's solving is it's fundamental to video, really. Copper cables just don't play well with high-resolution signals over long distances.
Not at all.
You try to run a standard DVI cable past, say, 50, maybe 60 feet, and you start seeing all kinds of problems. Signal degradation, pixel errors, flickering.
Yeah, the dreaded sparkles. And that's before you even think about environmental noise.
Exactly.
That noise you mentioned, the RFI and EMI, that stuff is just a signal killer in like a control room or any kind of industrial setting. So the DVI 7311, it doesn't really fight that battle, does it? It just goes around it.
It completely bypasses it. It takes that electrical DVI signal, turns it into pulses of light, and then you can send it up to 500 meters.
Which is, what, over 1,600 feet?
1,640 feet, yeah. And that conversion to light, that's really the key insight. It gives you essentially perfect immunity to noise.
Because it's light.
Because it's light. Fiber optic cable just doesn't care about electrical interference. You get an incredibly low RFI AME profile, which is why it's so perfect for those really sensitive applications.
And you're not giving up any quality for that massive range, right?
What's the maximum bandwidth you can actually push through 500 meters of fiber?
You get the full single-link DVI spec.
Yeah.
So HDTV resolutions up to 1080p, PC resolutions up to 1920 by 1200. It's running right at that maximum 165 megahertz pixel clock.
And how does it do that physically? What's the cable setup?
It's actually pretty straightforward. It just
Yeah.
needs 4 strands of standard 50125 multi-mode fiber.
Okay.
And it uses those little LC connectors. Each strand is basically carrying one of the essential signals.
Speaking of reliability, I know one of the biggest headaches on long runs can be the idiot handshake.
Oh, absolutely. It can be a nightmare. So does this unit just pass the signal along, or does it do something smarter with that EDID information?
It's much smarter, and this is a massive advantage. So, EDID is how your source device learns what the monitor can handle.
Right.
In a copper setup, that communication can be really fragile over distance. What this does is the transmitter module has programmable memory. It just learns the display's info once, and that's it. It stores it.
So it never has to ask again. It just knows.
Exactly. It ensures you get a solid, immediate signal lock every time. It just simplifies the whole installation process.
That's huge. Okay, so let's get a little more technical. The light itself, it's using 4 optical channels at an 850 nanometer wavelength. What's actually, making the light and catching it?
So the transmitter uses what are called VCSELs. That's vertical cavity surface emitting lasers.
VCSELs, okay.
And the receiver uses GS-PM1 photodiodes. Put simply, VCSELs are just these really common, efficient little lasers for these kinds of short-range fiber runs. And the photodiodes are super sensitive. They're designed to catch that 850 nanometer light pulse and turn it right back into a clean electrical signal.
So it's powerful tech, but we should be really clear about a couple of things it doesn't do. For you listening, this is a laser-focused, video-only solution.
That's right.
It does not support HDCP communications. So, no protected content from, say, a Blu-ray player.
Correct. No HTCP and also no digital audio. It's purely for the video signal.
Which is a trade-off, I guess, for the simplicity and the range.
It's a necessary trade-off to get that efficiency and that incredible distance.
Let's talk about power, too, because that always trips people up.
Good point.
The transmitter module, the one at the source, it can usually just pull power from pin 14 on the DVI connector itself, right?
Usually, yes, as long as the source provides at least 320 milliamps.
Mm-hmm.
But the receiver, the module at the far end, that one must have external power. It comes with its own AC adapter.
And the modules themselves are tiny, like an ounce each. Plus, they come with a 3-year warranty from DVIgear, which tells you they're built for pro environments.
They really are. So when you put it all together, what you have is the perfect solution for any application where you need flawless DVI over a very long distance. The noise immunity and the smart EDID handling make it, the go-to choice.
It really proves you don't have to throw out your DVI gear just because you have a long run to cover.
It dramatically extends its useful life.
It really does. So that leaves me with a final thought for you to chew on. The optical link in this system has a power budget of at least 9.0 dB. Now, if engineers wanted to push these specific 850 nanometer VCSEL systems even further, beyond that 500 meter mark, what do you think the next technical hurdles would be?
That's a great question.
What would they have to solve in terms of either optical efficiency or maybe receiver sensitivity before they'd be forced to just jump to a completely different optical solution, like a longer wavelength? Something to think about for your next extreme installation.